And we just said this, that one drawback of a ridge regression, it doesn't actually select variables and set things to zero when, as you said, in situations like that previous picture where things are small, it would be nice if they could just say, these are zero, we can forget about them. So the lasso is a more recent technique for shrinking coefficients in regression. It looks very much like ridge regression, but with one change. So here's the lasso criterion. Again, we have the RSS, as before. Now we have a penalty, but whereas before the penalty was the sum of the squares of the coefficients, now it's the sum of the absolute values of the coefficients. So it's a shrinkage towards zero using an absolute value rather than a sum of squares. And this is called an L1 penalty by analogy to the L2 penalty. The L1 penalty is just the sum of the absolute values. It's a norm, but it's called the L1 norm rather than the L2 norm. So what's the effect of changing this from a square to an absolute value? It's actually a small change, but it's quite important. Turns out that the lasso, like the ridge, shrinks towards zero, but it has the effect of actually setting variables, the coefficients of variables, exactly equal to zero when lambda is large enough. So it's neat. It shrinks, but also it does subset selection in a similar way to best subset selection. So it'll set coefficients to zero exactly if that feature is not important and lambda is large enough. So we say that there's a term for this. It's called sparsity. So the lasso yields what's called sparse models, models which only involve a subset of the variables. And again, it's a function of this tuning parameter lambda, which, as in ridge regression, we have to choose somehow, and we'll do so by cross-validation.
So, wow, the lasso seems like a really good idea. So clever. I wonder who came up with it, Rob.
Thanks. So Danielle was trying to embarrass me. So this is actually a paper that I wrote in 1996, and it's become, at the time actually, it was published and didn't get a lot of attention, but in the last about 10 years or so, it's become a very hot topic, both in statistics and computer science and other areas. And there's been a lot of work in sparsity in general, not just in regression, but the use of L1 penalties in a lot of different areas. I think one reason for its popularity now is computation. This computation is actually, this is what's called a convex optimization, so that's good news. And there's a lot of work in convex optimization, especially in the last 10 or so years, and along with the progress in convex optimization and fast computation, fast computers, people can solve this problem now, a lasso, for very large values of P and N.
And this has actually just been a fun thing that I've even seen. Like when I started grad school, you know, there was like one approach that statisticians were using to fit this model. And this was a famous paper that had just come out when I started, and it was written by Rob and Trevor and a few other people at Stanford in statistics. And then a new paper came out with a better idea, and then 20 more papers came out with better ideas for how to fit this model. And this has suddenly become something that anyone can solve on their laptop, no matter how big your data is, basically. And so it's just become an incredibly useful tool in a way that it even wasn't when I started grad school.
So we'll talk about GLMNet, which is an R library, which we use a lot in this book and in the book and the course, and we'll show you how you can solve a problem solve the lasso using GLMNet in R. Again, where the numbers of variables might be in the tens of thousands, you can solve it on a standard desktop computer in less than a minute. So we'll talk about the computation later on in the course. But let's first see what it looks like in the same example now. So again, the credit data set, and we're plotting the standardized coefficients as a function of lambda for the lasso. Again, we haven't talked about how to choose lambda, and that's going to be important. We'll use cross-validation. But let's for now look at the solutions as a function of lambda for all values of lambda. And now you can see, again, when lambda is small, we get essentially the full least squares estimates. When lambda is 0, we get exactly least squares, if I plotted this all the way to the left. And now as we increase lambda, we get shrinkage, as we did for ridge regression, but something special happens. At this point, for example, here, beyond this point, all these gray variables are the coefficients are exactly 0. Okay? Whereas for ridge regression, they were small, but they weren't 0. So it's actually, we can tell, it tells us you can throw away all these variables at this point and just retain these three, the blue, red, and orange. Similarly, this plot shows you the same thing in the other direction. So it's a combination of both shrinkage and selection of variables.
And so one thing that's worth mentioning is that in a lot of applications, selecting variables is actually really important because, you know, let's say I'm working with a doctor who wants to come up with a really good way to test for some particular disease. And he might start out by getting 30,000 gene expression measurements for patients with this type of disease. So he starts out with P equals 30,000. And he wants to find a really great model that can be used to test for this disease. But when push comes to shove and he's actually going to use this test in the clinic, he doesn't want a test that involves all 30,000 genes, because a test like that would be too expensive. It just wouldn't be feasible to actually use. But if he can get a test that works really well that only involves 6 or 8 or 25 genes, that could be a real breakthrough in testing for this disease. And so just from a practical perspective, the Lasso is just hugely useful because it allows us to efficiently find these types of sparse models that involve just a really small subset of the features.
You should be my personal salesman. You're doing a good job. But seriously, I mean, and Danielle is right. And I myself, I use the Lasso in schools and projects here at the medical school. And it's very satisfying to apply it and to see it helping scientists to find the signal in their data and come up with interpretable subsets among the thousands of features they present to me. So at this point, it might seem like magic. Why is it that just using an absolute value penalty gives us the sparsity property? Why do we get exactly 0? And I'm going to show you that in a picture. So let's think about that. First of all, we can formulate the problem in an equivalent way rather than putting a penalty. Remember, before I had the RSS plus lambda times the sum of the absolute values. An equivalent way to say the Lasso is to pose the Lasso problem is to say minimize the RSS with a constraint, a budget on the total L1 norm of the coefficients. Okay, so this is an equivalent problem in the sense that if you give me a budget S, there's a lambda in the previous formulation that corresponds to the same problem, and vice versa.
And by the way, if that looks like a total mystery, if you can reach back to your distant or not so distant past, if you ever took AP Calculus and you saw Lagrange multipliers in high school, this is really something that you might have truly seen in high school calculus a long time ago, but for simpler types of problems. Right. And this is just a more complex application of that same idea.
But in a way that its bound form is to me more intuitive than the Lagrange form, because think of it this way. Suppose you do full least squares and you get a certain answer. And now I tell you, and let's suppose the sum of the absolute values of your coefficients is 10. So you give me an answer, and I say, well, actually, I want to make your budget smaller. You've spent too much coefficient. So rather than 10, I want to give you a budget of maybe 5. So now I ask you to solve the same problem, but you're not allowed to use the coefficients as large as you want. The total budget you have is 5, and that's the bound here. So the Lasso is giving you a budget on the total L1 norm that you can spend, and within that budget you have to fit as well as possible. And as that budget gets smaller and smaller, the coefficients get smaller and smaller. If the budget is 0, the coefficients have to be 0. If the budget is large enough, you're free to use full least squares. But in between, the budget's going to trade off the size of the coefficients with the fit. So I think it's quite an intuitive way of looking at these problems. For ridge regression, you get exactly the same analogy, but now the budget is in terms of the sum of squares. So again, this is equivalent to the Lagrange formulation for ridge regression we saw earlier. But the reason I want to bring this up is this following picture, which helps to explain why the Lasso gives sparsity. So on the right is ridge regression, and on the left is the Lasso. Now this is a bit more mathy than most things in this course, but hang in there, and I think if you do, there'll be some payoff. So this picture is ridge regression. So what's going on here? First of all, P is 2, so there's 2 coefficients. And I've indicated here the full least squares estimate. So if there was no penalty, I just did least squares on the 2 variables, I'll call the solution beta hat, and that's this point. And now the sums of squares in the RSS, the contours of that function, in other words, it's lowest here because that's the least squares estimate. But now as I move away, if I think of this like as maybe a cereal bowl, and I slice the cereal bowl, here are the contours. So here's the value at which RSS is a bigger value. This next contour is a higher contour of RSS. So these are the contours of RSS as I move away from the minimum. Okay? And this is the constraint region. Remember, in ridge regression, and this formulation here says, you have a budget on the total sum of squares of the betas. So the budget is the radius of a circle, right? Here I have a fixed budget, and so in words, the ridge problem says, find me the first place these contours hit the constraint region. In other words, find me the smallest RSS you can get within the budget defined by this circle. That's ridge regression. And the solution in this picture is right here. So this is the ridge estimates for this budget and the data, this particular data, and the data is determining the shape of these contours and the location of beta hat. So ridge regression says, find me the first place the contours hit this constraint region, it's this solution. And you can see because the constraint region, the sum of squares, is a circle. This is where the sum of squares of beta 1 and beta 2 is less than a budget. It's a circle, right? And unless you're very lucky that you're not going to hit exactly at a place where one or the other is 0. Right? Now let's move over to the lasso. Same picture, least squares, same thing. The sum of squares function is the same, all the same up here, but the constraint region is now the sum of the absolute values. So rather than a circle, it's a diamond. A diamond has corners. So in this picture, I've hit this corner, and now I get a place where beta 1 hat is 0. Right? So here's the lasso estimate. So in other words, to summarize, the absolute values give you a constraint region that has sharp corners, and high dimensions you have edges and corners. And along an edge or corner, if you hit there, you get a 0. So this is geometrically why you get sparsity in the lasso. So here's, here's our case. First of all, return to the example where we had 50, let's see, 45 variables, and they all had non-zero coefficients. So now I'm looking at comparing the lasso to ridge. So on the left picture, for the lasso, we see the bias, variance, and mean square error as a function of lambda. And on the right, we've superimposed the biased, variance, and mean square error of ridge regression with a broken line and the lasso. And we can see that overall, so again, the solid line here for mean square error is the lasso, the broken line is ridge. They're very similar. Ridge is a little better, perhaps, right? So we don't do much better. We don't do better at all with the lasso here. And the reason is that we've got, the true model is not sparse. The true model actually involves 45 variables, all of which have been given non-zero coefficients in the population. So it's not surprising that we don't do better than ridge in this case.
And one thing we should mention is on this right-hand panel, the x-axis is something we haven't seen before, which is the r-squared on the training data.
Right.
And the reason we have that x-axis is because in this figure on the right-hand side, we're plotting both ridge regression and the lasso. So it wouldn't make sense to show ridge regression and the lasso with lambda on the x-axis, because the lambda means two different things for those two models. So when we look at r-squared on the training data on the x-axis, that's kind of a universally sensible thing to measure, regardless of what the type of model is. So
you must have drawn this picture in the book.
yeah, I made this picture.
It's a beauty.
Thank you, yeah.
Okay, I would have noticed that detail otherwise. Okay, so now here's a situation where we do perform better with the lasso, and this is a case where now in the population, only 2 of the predictors have non-zero coefficients. So the previous situation was dense or non-sparse. This situation is sparse. There's only 2 predictors in the true model that are non-zero coefficients. And now we can see what happens. Well, the lasso's mean square error here is minimized for quite a large value of lambda because it wants to make the model sparse, as it needs to. There's only 2 non-zero coefficients. And now when we compare the lasso to ridge, remember ridge is the broken line and the lasso is the solid line. You can see we do quite a bit. Here's the lasso's mean square error, and there's ridge is here. You can see we're doing quite a bit better using the lasso in this situation. And again, it's not surprising. The true model is sparse, so it pays to use a technique which encourages sparse models coming out of its estimation. Whereas with ridge, we don't get a sparse model, we get a dense model. So in conclusion, comparing these 2 techniques, as is usually the case in most things in statistics and science in general, there's no simple rule that means that you should always use one technique over another. It depends. You always hear that from statisticians. It depends. Well, it depends on the situation. In this particular case, if the true model is quite dense, most predictors have non-zero coefficients. We can expect to do better with ridge. If the true model is quite sparse, only a few coefficients are non-zero, then the lasso can be expected to do better. course, we don't know that usually. We hope, actually, that things are sparse because life is simpler then. But going into a data analysis, we have no idea whether the true number of coefficients, non-zero coefficients, is large or small. So we use, it's typically good to apply both methods and to use cross-validation to determine the best model coming out of each method, and then compare the cross-validated error for the two methods.